Hey everyone. So I just sort of wanted to go through one of the contests for I think
Everyone. So I just sort of
just gonna mute myself. Cool. Yeah. One of the contests for converts around 740 or 784 to 4. And I just want to walk you through all the different problem solving strategies you need to solve the problems on your own. Right? So let's be clear about this. Let's say you took this contest in actual contest. And in contest, you were only able to solve, say, like 3 problems. Chances are you're not going to be able to solve all the problems and with the solution, right? You're not going to solve all the way up to 8, and that's okay. What you want to shoot for is solving 2 more, upsolving like 2 more after the contest, which means upsolving, which is what upsolving means, sorry, that you did in contest. So if you solved A, B, and C in contest, you want to try to solve D and E after. And this way, you're not going for problems that are like super harder than what you did in contest, but they are somewhat harder. And I guess for this contest specifically, E is harder than F. So you might want to go for, say, D and F. And specifically, I'll be walking through like the problem solving process, right? So obviously, it's good if you know how to solve the problems. But more importantly, what you want to learn is the process that you need to think through so you're able to solve the problems on your own, right? Because, yeah, and because like the same problems probably not going to show up again, but the problem solving skills will show up over and over again. And I have not seen any of these problems before, so I'm just going to read through them with you, and let's go to it. All right, CodeForces separates its users into 4 divisions by their rating. Rating 1, rating 2, rating 3. Given a rating, print which division the rating belongs. Okay, so this is more of a how to code problem. This is div 4. This is kind of what you would expect. Oh yeah, and after the live stream, what I'm going to do is I'm just going to like say problem A at this time, B this time. So it probably was up on the screen earlier. Just skip to the problems that you want. No need to read through every single problem. Okay, cool. So yeah, we were told all these ratings. So this may seem like a simple if problem. However, we have a number of test cases. So one thing that helps people in this level is the idea is the number of inputs that you read. Just try to get that number correct and try to make the number of outputs that you print correct also. So in this problem here, note that the number of inputs you read is going to be the first line, and then description of each test case contains 1 integer rating. So this is going to be T lines here. So the first thing we want to do is make sure we're reading the correct number of inputs. This will solve 50% of your problems at this level. So I'm just going to code all my stuff in C++, and I'm not using a bunch of defines I usually do, so forgive me if I make some bugs. You have to come back and fix them, but it'll all work out. All right, the first thing we have is our variable T, the number of test cases. And we're just going to read in T. Okay, so now we know that there's T plus 1 lines of input. So after we read in T, we need to read in the next T lines of input. So for that, we're going to do a loop. And then what do we want to call this value? I'm just going to call it rating. Okay, now how many lines of output? Well, for each test case, we want to output a single line containing the correct division. So this means we want to output T lines of output. So what this is going to look like is we need to do one output. Something here. Let's put this as a comment right now. So we need to do one output in this loop. Okay, so now this gives you a general structure, right? This is we're reading in our input, and this is we're putting our output. Now what we want to do is obviously calculate what we're trying to output. So those are going to be essentially your 3 steps for a problem like this, right? Step 1, read in the input. Make sure you're reading the correct number of lines of input. And you can do that by counting the number of lines which you get and number of rounds you have. Step 2, count the number of lines of output to make sure you're outputting the correct number of items. And then step 3, try to figure out what to output. And the reason we figure out where to output before we figure out what to output is because a lot of times figuring out where to output could help us figure out what to output, right? For example, if we were going to output something here, well, we have a new rating for every single loop. So then it probably wouldn't have to do with the rating we get inside every loop. But we don't. We have to output here. So, all right, for division 1, if it has a rating of less than 1900, so we can just do the statement for this, or less than equal to 1900. And to see out something here, we're going to put that in our if statements, right? So I'm just going to remove this, and we can just put the see out problems here. See out. Else if. So here we have the rating between 1600 and 1899. So obviously we could do this in for those who are more advanced, else if rating is greater than equal to 1600. Oh, sorry, this should be rating is greater than equal to 1900, not less than equal to, because here rating is on the greater than equal side of this. So yeah, for those who are more advanced, you could probably just do else if rating is greater than equal to 1600, but there's no reason you can't do greater than equal to 1600 and rating is less than equal to 1899, just as the problem statement says, less things to think about. Just do it directly as it says, right? Greater than equal to 1600, less than equal to 1899. And then see out division 2. Else if, again, you can just do rating greater than equal to 1400, but there's no reason you can't also do and rating is less than equal to 1599. And note that this double thing here means and. So it'll, if this is true and this is true, it'll do whatever is in here. And obviously in the last case, rating less than equal to 1300, you can do an else or you can do an else if. Just gonna do else, division 4. Oh, 9 division. All right, and the reason that else works is because if none of these is true, then the rating has to be greater than 14 or less than 1400. So it has to be in this category. All right, how do we test our code? So the way I like to test the code is I have a file in my folder called test.in. And I'll just copy the input into test.in. And I say if stream cin test.in. So what this does is so cin is what we want to do for standard input output, as we were going to have for this problem here. But to use the file, well, we're going to call the file cin. So essentially what's happening is as soon as right now it'll read from the file, but when I submit, all I have to do is comment out this line, and then it's gonna read from standard input output. So I'm just gonna run this. Let's see, I think it forgot to make it. This is just the way I do. For some compilers, the brackets work. For mine, it does not. So I made a file which has this, but don't worry about this. This is a small thing. All right, just gonna clear terminal here. Okay, it's still not running this. One sec. All right, I'm just gonna delete this. Main.java exists, so it was making main.java. Okay. Okay. I'll just run the wrong thing. All right. Sorry about that. All right. So this is going to run the code here. Okay. So we're in our code. So let's just make sure that it's printing out everything we want. It says 4444 321. Perfect. So now we can just comment out the stream and I have a lot of random stuff, but that's okay. Perfect. All right, we got problem A. Any comments so far? Nope, we're all good. Okay, now let's go on to problem B. Given an array of n elements, print any value that appears at least 3 times, or print -1 if there is no such value. All right, so let's restart this. And yeah, you could probably reuse some of the code, but just because some people might want to be picking which problem they start on, I'm just going to restart this from scratch. Okay, so as I said previously, the first thing we want to do is make sure that we're reading the correct number of input values, right? This is a little bit more advanced problem. Some people, more advanced people doing it, but you still want to make sure that that's the first and foremost thing. So the first thing we read in is our input t. Then the first line of each test case contains, so when we say each test case, that means we need to loop through all possible t test cases. Okay, so then each test case we will solve here. The first line contains an integer n, which is the length of the array. Speaker mic set up a little better. Okay, there we go. So we have int n. Let's read in n. I actually like to do my n uppercase, so I'll just do that. But it's a personal preference. Uppercase, lowercase doesn't really matter. Then the second line contains n integers. It's the second line of each test case. So again, this is each test case means it's still going to be inside the loop where we do each test case. So n integers, the elements of the array. So let's make an array, okay, with n integers. And what I like to do actually for my arrays is I'm going to create them globally. And I'll explain why in a second. And the size of the array, since it could have up to n integers and n is up to 2 times 10 to the power 5, we will just make a 2 times 10 to the power 5. And again, 10 to the power 5 means we're going to have 5 zeros and 2 times 10 to the power 5. So 2 followed by 5 zeros. All right, the reason I do this is because it uses a little bit less memory than, well, I guess in this case, like the sum of all n over all test cases is honestly 2 times 10 to the power 5. But like if this were to be a higher number, like say the sum was to be like 5 times to the power 5, if we make it locally here, it'll create a new one each and every time, a new array A each and every time, and the sum gets really big. If we create it globally, it only creates it once, and we can just reuse the array. Obviously, we could make n global too and also just reuse it, but n doesn't take up too much memory. A does. Like in this problem, a little bit less so because this value and this value are the same, but it could be a more complicated problem. So it's just a good habit to have. Like in general, this will be a decently good habit for you to have. All right. So now we need to make sure we're reading in the correct number input, right? So we need to read in all of the A of n. All right, so we read in all of our input. And then for each test case, print out any value that appears at least 3 times or -1 if there is no such value. So for each test case, we're going to output 1 value. That's our second step. The first step is making sure we're reading in the correct number of inputs, which we are doing here. Second step is print the correct number of outputs. And third step is figure out what you want to print. So we figured out the correct number of outputs by just printing 1 value here. So for every test case, we'll print 1 value, and that's the correct number of outputs. That's the correct number of what we were printing. Okay, so now how do we figure out what element appears 3 times? Well, there are several ways to do this, but I'm going to give you a decently interesting one. So in this problem, they don't give you a cap on the biggest element that can appear. Just making sure of this. Oh, they do. every element is less than or equal to n. Okay, so the biggest element that can appear is 2 times to the power 5. So then there's going to be a couple of different ways to approach this. So here's the problem-solving strategy that you should probably learn for this problem. And the reason I say that is because I am focused on problem-solving strategies rather than the solution to this one specific problem. Let's get whiteboard up here. Okay, so your problem-solving strategy here is going to be draw a bunch of test cases by hand and try to solve them by hand. And try to notice any patterns. So let's just say we had a test case which has the values 1. Actually, let's. Oops. Get that here. Okay, so let's say the test case has the values, like 5, 3, 3, 1, 1, 2, 9. Okay, and I asked you, hey, looking at this, does any values appear 3 times? Which values appear 3 times? We might look at this and be like, I have no idea. This is just way too complicated. So I'll tell you the answer. The answer is 3 appears 3 times. And 2 appears 3 times. Right, so there's 2 possible values, but you couldn't tell that by just looking at this. So let's go back to problem solving strategy, right? It was to do a bunch of things by hand and see if that helps us. So let's try to solve this by hand. How would we come to the conclusion that the answer is 3 or 2? Well, we might say, okay, I see the value 5, then 3, then 1, then 1 again. And you might need some sort of data structure to keep track of what you've seen before, right? So you might say, oh yeah, I saw a 5, and then I saw 3, then I saw 1, then I saw another 1, then I saw 2, then I saw 9, so 10, 11, 16, 15, 17, 4, and you see 3 again. Wait, did I see 3 before? You have to look through all of these values to see if you did and be like, oh yeah, I did. Let's see 2. Did I see 2 before? Look through all of these. Oh yeah, I saw 2 before. This might not help you too much by hand, especially if you have a lot of values. So you think, okay, can I be a little bit smarter with this? Well, I see 5, I see 3, then I see 1, see 1. If I put the 2 here, if I put the values in order, it's easier for me. Because then, I see 9, 10, 11. I really quickly can tell if I've seen a value before. What do we say? Have you seen 4 before? Well, no, I've not. Between the 5, there's no 4. So 16, 15, 17, 4, 2 or 3, then 2, then 9. It's the second 9. I didn't even notice that earlier, right? And now we notice it. It's the second 10. 11, 15, 20, 21. I see 4, 3, 2. Okay, so from here we can see that clearly 2 and 3 are our answer, right? So what did we do to come up with something like this? Well, we solved it by hand. We tried to find some way to make it really easy for us to do it by hand. Now, here I just did 1 test case, but your problem solving strategy is actually going to be try like 6 or 7 test cases. And when I do problems, I try to solve I do about 15 plus test cases by hand, sometimes like even 30 plus, because this is the easiest way to try to notice patterns. How big test cases do you want to create? You want to create as big as you can reasonably solve by hand. So, for example, 100 you can't solve by hand. If this was a different problem, you may not even be able to solve this big thing by hand, right? This is a pretty big test case. But for this problem, you can't solve the test case by hand. So keep doing more and more test cases. Try to find more and more ways to make it easy. And yeah, that will be your strategy for this problem. And so what do we get from this? Well, we just want to sort the values. And once we sort the values, we'll look for consecutive values, right? So once we sort this, we'll get something that looks like 1, 1, 2, 2, 2. I'm not going to write out the whole list. You get the idea. So once we sort it, then we can say, okay, are there 3 consecutive of any value? And if there are, we're good to go. And the 3 consecutive, by 3 consecutive, I mean like 3 values next to each other, which are the same. Because there can't possibly be a 2 here, and then also a 2 like after the 9s. It doesn't happen like that. If there's going to be 2s, they're going to all be next to each other in the sorted list. So we can just implement that. We need to sort A, so we'll just sort A, comma A plus N. Now we need to see if there's 3 values next to each other. What's the easiest way to do that? Well, we'll just loop through the entire array, and we'll check that. So let's first start with a simple loop. We'll loop through every single value in the array. Now, what would be the easiest way to check this? Well, we can see if the value equals the one after it and the one after that. All right? So we can say if A of j equals A of j plus 1. So that means if this 2 here equals this 2 after it, and it equals the one right after that too. So and A of j equals A of j plus 2. Then we found the answer. Okay, so what do we want to do in this case? Well, we have the answer, and we'll deal with how. Let's just say we have a variable int answer. We're going to set out the answer at -1, and we'll set the answer equals A of j here, because A of j is a value that appeared 3 times. So why do we start the answer at -1? The reason is, if there is no answer, we print -1. So if the whole loop does not find the answer, doesn't update it, it's going to print it's going to have -1 as the answer, which is perfectly valid. Okay, now let's go back to this loop here. Originally, we said we're going to loop through all the values, but notice we're looking at A of j plus 2, and if this one, okay, and if j is the last value in the array, right? Let's just say our array was just this big. If j is this last value, as you might notice, j plus 2 doesn't exist. If j is here, j plus 1 exists, but j plus 2 doesn't exist. If j is here, then j plus 2 exists. So we have to make sure j plus 1 and j plus 2 exist, so this is going to give us an issue. In Java, this will give you an out-of-bounds error. In C++, this won't even give you an error. It just will do random stuff and break your code. It may not even break it for the sample, so we're not even able to catch this, which is really annoying. So we want to make sure we don't do that. So the question is, do we need to test this for the last 2 values? Well, if we're at the last value in the array, let's say we did have 3 9s, right? We want to catch this. What's going to happen is when we're looping through this 9, it'll look at A of j plus 1, A of j plus 2, and it'll catch the sequence. So when we're at this 9, we don't need to look at the last value. When we're at this 9, we don't need to try to look at j plus 1 and j plus 2. We only need to try to look at for the second to last value and before. So for that reason, we'll loop through 0 to n minus 2. And we're going to output 1 value, and that's going to be answer. Okay, so let us test this out. All right, let's compare these. We have -1, 2, 2, 4, 3, -1, 4. Perfect. So then we'll just comment out this so that we're reading standard input output. And .cpp submit. Nice, we got this problem too. Cool, let's move on to the next one. Oh, let's first check if we have any questions. Someone said hi. Hi, Paul. If you have any questions, again, just dump them in the chat and I will get to them. All right, problem C. Given an, let's remove what we have so far. All right, given an array of n positive integers, you can do 2 operations on it. Add 1 to every element with an odd index, and add 1 to every element with an even index. Looking through the examples, this makes sense. Now note that they don't have a of 0, so the first element is a of 1. Okay, this is good to know. So this basically means that but I'm just walking through my thought process here, right? Basically means that if we have, because when we're going to do it, we're going to call this index 0, then index 1, then index 2. So their definition of odd is going to match when we say is like 0, and when we say 2 is what they're going to say is 3. So the definition of odd is going to match our definition of even, and vice versa. But that's okay. Just a small thing to keep in mind when we're coding. Determine if we have these operations. Determine if any number of operations would make it possible to make the final array contain only even numbers or only odd numbers. In other words, if you can determine if you can make all the elements of the array have the same parity after any number of operations. Okay, so this is going to be the exact same problem solving strategy that we did last time. We're just going to try. We're just going to try a bunch of sample test cases by hand and see where we get. So let's just say that our input is 1, 2, 3, 4, 5, 6, 7, 8. Why not start here, right? Good starting point. Can we make all of the odd ones odd? Or sorry, can we make all of them odd or all of them even? Well, if we add 1 to all of these, I'll call them odd places, what we're going to get is 2, 2, 4, 4, 8. So this works. Okay, what if we had the array 1, 1, 2, 2? It's possible. Now, again, you're going to have to do a bunch of arrays of different types, as big as you possibly can. I'm sort of like picking special ones because I kind of have an idea what the answer is. But for your problem solving strategy, it's very important that you do a bunch of test cases by hand, because it's not going to come to you. Like, the answer is not going to just magically come to you if you just sit there and hope the answer comes to you. Fortunately, that's not how life works. You have to actually do work to get to the answer. And so your work for this problem is going to be just doing a bunch of test cases by hand. But yeah, what you might notice for this input here is consider just the odd numbers, right? We have our odd indexes. We have 1 here and 2 here. If we add 1 to this, we're going to have 2, 1, 3, 2, right? I'm just going to put x's here. Just consider these two. If we add 1 again, we're going to have 3, 4. And this is never going to work. When just these two values itself are never going to have the same parity. Okay, so then the next step is once you do this, once you make the test cases and you notice a pattern, like you notice, this is not even a pattern, you just notice something. The question is, what you do next is you ask yourself why. So we did test cases, we noticed something, we noticed this is not working, this is not going to happen. But ask yourself why. Why is this not possible? And what we might notice is, well, since this is even and this is odd, if we add 1, this will become odd, this will become even. If we add 1 again, this will become 4 even, this will become 5 odd, right? Oops. And so if one of them is even and one of them is odd, and we just keep adding to both of these values, they're never going to become the same parity. And the same we find might hold for like this second location, the second 1 and 2 location. Right? So this here is gonna give us an idea that we have to check if all of the odd values have the same parity, then we can make all the odd values odd or even, however we want. And the same thing, if all of the even values have the same parity, we can make all the even values odd or even, right? So if we have something like this, actually, where all of the odd ones are odd and all the even ones are even, we can make this work. But if this one here were to become a 7, now we can't make this work. Because now this 6 and this 7 will never have the same parity. Okay, so let's walk through the coding process. We can just, and yeah, I should clarify. I will tell you right now that is essentially it to the algorithm. Just check if this is possible. And in order for you to convince yourself of this, right, what you should do is you should continue walking through the process. So continue developing more test cases and solve it by hand until you have a solid idea of why. But essentially what you're going to find is that if we have 2 even numbers and we add 1 to them, they become odd. An even plus 1 equals odd. And same thing, odd plus 1 equals even. So we can think of the even numbers and odd numbers separately, right? If we want to get all of the ones that even locations to an odd number or an even number, I guess this is sort of weird because the numbers are even and odd and the locations are also even and odd. So let's say if you're trying to get all things from one set of locations to be an odd number, if they're all odd, you're already done. If they're all even, you just add 1 to them and they're odd. And same thing if you want to get all things from the other location to be an even or odd, right? So if they're all the same, if they're all odd or all even, you're good. Otherwise, the answer is not possible. The answer is no. All right. So let's first read on the input. First line contains t, the number of test cases. Oh yeah, let's do a runtime analysis. We have not been doing runtime analysis for the previous problem. We probably should have, but that's fine. We'll do runtime analysis for this problem. Okay, so what is the runtime of this? Well, we can check all the odd locations and see if they're the same parity by doing a simple loop, right? So this will take us O of n to do. And we can check all the even locations, see if they're the same parity, also by doing a simple loop. So let's call it n plus n, and we'll get to the big O later. So yeah, we'll check all the odd locations in O of n time, all the even locations also in O of n time. So we can check one test case in O of n. Now we have t test cases, so our overall runtime is going to be t times n, because we have to do this for every single test case that we have. So what is the value of t? It's going to be 100 and n is 50. So 100 times 50 is going to give us 5,000. Now note that we can do about 5 times 10 to the power of 8 operations if we're using C++ on CodeForces. It's closer to 10 to the power of 8 if you're using Java or Python. But in either case, 5,000 is more than small enough. So this will work. Cool. Well, let's just actually... All right, let's just... I'll put this back later. All right, so let's just run our code, and we'll look at our code and the runtime analysis a little bit later too. So the first line is t, the number of test cases. So let's read in t. And then each test case will have this and this. So then we need a loop. If we want to do anything for each test case, we need to loop through all the test cases. We're going to put everything for each test case here. Okay, the first line for each test case is n. How are we going to make all the variables global? For the same reason we talked about for the previous problem, just because we want to make the array global. So second line contains n integers, the array, or AI, all the values of AI, so we'll just make an array A. And the maximum length of the array is n, which is 50. So we're just going to make it of size 50. And it's for each test case. So of course, we're going to read it inside this loop, which is for each test case. Okay, now so first step was reading on the input, right? Second step is going to be determine where to do your output. So we have the correct number of lines of output. So the correct number of lines of input, we have the correct number of output. So output t lines, 1 for each test case. So we will do this in the loop, which goes t times 1 line of output goes here. Cool. So now we need to figure out, the third step is figure out what the output should be, right? And that we determine our algorithm for that here. So first we're going to check all the even ones, and we're going to determine if the odd locations, so like the first, third, fifth, seventh, so on and so forth. And we're going to determine if they should be which parity, like if they're even or odd values. And so we're just going to look at like a of 0, right? And this will tell us what a of 2, 4, 8, 16, all of those should be. Now note that we are saying 0 here, and they're calling the first element a of 1, kind of like we were talking about at the beginning. Don't worry about it. Let's just call this first parity to keep it simple. Okay, so how do we loop through all the odd values, right? I'll call all the odd values. So the first value is going to be 0. We also want to make sure our values don't go above n. Okay. I think I use lowercase in here. Now, what values do we want? Well, we want 0 and then 2 and then 4, 6. So instead of doing j plus equals 1, we'll just do j plus equals 2. So every time we're going to add 2 to the previous value of j, and this will give us our sequence. Okay. And then we're also going to have our answer. And we're going to start it out as no. And the reason, or sorry, is yes. And the reason is, anytime we find that, these values don't have the same parity, or these values don't have the same parity, then our answer is going to become no. But until we have that evidence, we're going to default to yes, because the answer is yes if nothing bad happens. So we're going to say, let's assume nothing bad happens. Then we're going to check. If there is something bad, we'll change it. The answer being no. But the default is the answer is no until something bad happens. Okay, so we're going to check. Does something bad happen? Now, how do we figure out if value is odd or even? That's a good question. So what we're going to do is we're going to take the value. Let's say our value is 10. Okay, let's say we divide this by 2, right? We're going to get 5, and the remainder is going to be 0. If we do 11 divided by 2, that's going to be 5, remainder 1. And what you will find is if you take an even number and divide it by 2, the remainder is going to be 0. And if you take an odd number divided by 2, just take like 1 more than the even number, it's going to have the same value, but just a remainder of 1 instead of a remainder of 0. So what we're going to do is we're just going to take the value, divide it by 2, and check the remainder. And in coding, whatever language you're using, is something called modulo. This does this for this, which is this percentage sign. So if we say, 10 modulo 2, this will give us 0 because the remainder is 0. If we say 11 modulo 2, this will give us 1 because the remainder is 1. Okay, so let us go here. We're going to say if a of j modulo 2. So what do we want this to equal? We want this to equal the same parity as the first value. So we're going to set this to what the remainder should be. So if the first value is a 1, then the remainder here is going to be a 1. So now it's going to check 3, 5, and 7, see if they all have a remainder of 1. So this equals, or is not equal to first parity, because we're checking if something's bad happened, right? We're assuming there's nothing bad, we're checking something bad happened. And this is bad. So then our answer is going to become no. Otherwise, we're going to assume everything's fine. Right, and we do the same thing for the second parity. So we see this 2, which is going to set the remainder to be 0. And we see this 4, we check the full 4, remainder 2 is also 0. So we set a 0. Check, it works. 0, check, this works. 1, oh no, the 1 doesn't match with the 0. So it's going to say that something bad happens here and that the answer is no. Now this was an 8, then I would say that there's nothing bad and the answer is yes. To clarify, this doesn't actually, it worked when it was 8, not when it was 7. All right, so I'm just going to copy paste most of the code. Actually, let's just rewrite the whole code. Okay, this is what the remainder should be. Now, where do we loop? Well, the first index we're going to do is 1, right? So we did 0 previously. We're going to do 1, 3, 5, and so on and so forth. So let's sort it out as 1. And we still want to make sure we don't go bigger than n. And we're still going to do plus equals 2 because we add 2 every time. It's going to be the same thing. If a of j mod 2, this is what the remainder is. If it's not equal to what this should be, second parity, then the answer is going to be no. All right, so we have our answer now. So our side is yes, but if anything bad happens, it's no. And we just see out answer. Okay, and that should be our code. So let us test it. All right, it gives us yes, no, yes, yes, which matches what they have. Let's just say calculate the runtime one more time. So earlier we calculated the runtime is O of n times or t times n. We're using lowercase n for this problem, so we'll just keep using that. Now, another way to check the runtime is to check what loops we're going through, right? So here we have a loop of size t. Here we have a loop of n. Here we have a loop of n over 2, essentially, and here we have a loop of n over 2, right? So it's going to be, every loop is going to be multiplied with the loops that are inside it. So here we have t and n inside it. That's going to be t times n. Here we have t times n over 2 inside it. That's going to be t times n over 2. And here is also t with n over 2 inside it. So again, I'm not going to teach runtime here in this video. I'm expecting you already know what runtime is and you already know what big O notation is. If you don't, you can look that up. I'm also in the video on it, I believe. I don't remember exactly. But yeah, I'm not teaching runtime here, but the idea is if you know what big O notation is and how it works, when you add all these up, you're going to get O of t times n. And if you don't know what runtime is, again, just Google, look it up, try to learn it, or ask on CodeForces, ask me about with this video. Either way, and yeah. All right, so we have this test case that works, and we have a runtime that we verified matches what we originally thought of. So let's submit this. Cool, this worked too. All right, let's check if you have any questions real quick. Please keep making such contest solving videos. Your arguments are easy to understand. I'm glad you like it. That's kind of the goal. I'm happy you like these. Is there anything specific that you think makes it really easy to understand? Let me know so I can keep doing that. If there's anything you're like, hey, you can fix upon this part is a little hard to understand, let me know that too, so I can also improve upon that, right? Oh, working on that. You seem to enjoy competitive programming. Why do you not participate on CodeForces? I have a lot of things going on right now. School, I run vPlanet, I go to MIT, so I have a lot of things to keep up, but I will get more and more into CodeForces now that I have a little bit more time over summer. All right. Let's see. Next problem. Colorful stamp. Oh, they got colorful problem statements. Cool. A row of n cells is given, all initially white. Using a stamp, you can stamp any two neighboring cells such that one becomes red and the other becomes blue. A stamp can be rotated. It can be used in both ways, such as BR and RB. All right. During use, the stamp must fit on the end cells. It cannot be partially outside the cells. The stamp can be applied multiple times to the same cell. Each use of the stamp recolors both cells that are under the stamp. So it looks like stamps only do two things, as they kind of said here too. For example, one possible sequence of stamps to make the picture BRBB could be you start with a white, and then you stamp these two, and then you stamp these two, and then we stamp these two. All right. Given the final picture, is it possible to make it using the stamp 0 or one more time? 0, using the stamp 0 or more times. Okay. This is a bit of an oddly worded problem. Probably could have been phrased better. Honestly, if I was running this problem for starters, they could start off by saying what your end goal is. Like when I was reading through this entire thing, I was like, all right, cool, but what are we doing with, like, why do we care about these stamps? So starting with something like this might have been helpful, but that's fine. I think I'll have to point of the picture now, or point of the problem now. So let us start working on this. Okay, so your problem solving strategy for this one that I'm going to give you is, and I should mention that, like, you're going to have a bunch of problem solving strategies. You're going to want to try all of them on all the problems. And the unfortunate reality is that not all of them are going to be useful for every single problem, right? The try a bunch of test cases thing is useful for many problems, but not 100%. And the one I'm going to give you for this one, again, useful for many problems, but not 100%. And the idea is, like, why do people spend hours on problems? Because you're just trying different things, and something's going to work. And as you get better and better, you're going to have a better intuition of what sort of things are going to, what sort of strategies are going to work better and better. But you know, at the end of the day, if you just want the solution to land in your lap, it's just not going to happen. You're going to try a bunch of things. Some things will work, some things will not. And people who end up solving the problems in contests are the people who tried a bunch of things until they found something that worked and stuck with it. So the one I'm going to give you for this one is ask a bunch of questions and try to answer them. And this is sort of similar to the last one in terms of like, we're going to create test cases for these questions that I'm going to give you examples of, but you don't always have to. But these test cases are going to be specific ones. Like we want to try different edge cases. So the first edge case we're going to try, and I'm going to throw it to you, is it possible to have a string entirely of bees? Is this possible? Okay, what does this do? What does asking this question do, right? It makes you think about the problem and it makes you come to some observation. Like you're going to get more information about how to solve this problem simply by answering this. Because at least it'll give you, in this case, the answer is no. Right? You can't make all these. And so we get a little more information about when the answer is. We get a little more information about the answer. Similarly, is all reds possible? Which is also not possible. Okay, so we determine that all B's and all reds is not possible. What else do you want to say? Well, is it possible to have, some whites and then like a red and some whites after it? This is also not possible. Similarly, there was like some whites in a B. Even if the B was at like an endpoint, it's still not possible, right? Okay, so we have, there's a label on top because we're going to be asking this about a bunch of different things. All right, what if we have something like, so we determine this is impossible, right? If we have something like some whites and then some like sequence of R's and B's. We have some whites, another sequence of R's and B's, then some more whites. And this comes back to our first strategy of like solving several examples of this by hand. But I guess the question here is like, what does this do for us? And solve a bunch of these by hand. We definitely want to do that. You don't pause the video and go do that. What you might notice is that obviously the SAMP can't paint white. So this sequence and this sequence are distinct, meaning they're solved separately. And where do we get this observation from? Well, this follows from this previous question we asked about this, right? When we determine that there are in the middle of a bunch of whites or the B in the middle of a bunch of whites is not possible. It's because everything in between the whites is like a whole nother sequence in itself. So whenever we have any like a white, everything before and after is like a separate sequence. Okay, what does this do? Well, this observation leads us to the fact that now we don't have to care about whites. Yay, we removed the whole entire letter. Because we'll just solve everything in between the whites, and every white is obviously possible to make. So now we can only consider sequences which have R's and W's, R's and B's. Cool, so we'll determine that this here is not possible. And we determine that this is not possible, which means like a single R or a single B is also not possible, right? What else can we determine? Well, what about the sequence? What if you have like an RB? Well, this is possible. We have like an RBR. Can we make this? Well, let's try it, right? This is not as obvious an answer. So let's think about this. We can do a stamp, which goes RB. And we'll just have like RB white. And then we can do like a BR stamp here. And then we'll have RBR. And we can make this. Okay. And similarly, this means we can make BR, and this means we can make BRB. Be right back. It's funny. So we can make all sorts of stuff, right? In terms of like what I should point out here, we can make these two, right? What if can we make BB? What's already said no, and RR we already said like no. But let's look at these three sequences. Let's say it's just not one color. What ways are there to? What are all the different three sequences? other than the ones we know we can't do, which is RRR and BBB. But we're gonna do these two. Let's see, we're gonna have BBR. So there's gonna be 2 to the power of 3, 8 sequences minus these two, right? So we're gonna have BBR, BRR, BRB, RBB, RBR, and RRB. Okay, so these and this, these are our 8 possible sequences of 3 letters. So let's think about these, right? I'm just gonna circle these. So we already said we can make these two, RBR and BRB. That's this and this we can make. All right, can we make this one here, RRB? Well, yeah, we can, we can do white RB. And then, well, this one's gonna be a little harder sequence. Let's undo that. All right, we can do RB white. And then we can stamp this with R and this with B. And we'll get RRB. This we can also do. And it's like we can do RRB, we can do a symmetric one, which is BBR. And BRR is just RRB backwards. So we can also do this, and we can also do the symmetric one of RBB. So we can do literally all the sequences except for the ones which have 1 letter for a length 3. And we determine this by brute forcing all 8 of them. Interesting. Okay, now what if we have something of length 4? That's a completely new problem. It's gonna be like 16 of them. And we go length 5 is gonna be 32. So it's not gonna be practical to just keep increasing the length by 1. But what if we do something a little more interesting? What if we ask the question, can I convert a sequence of length 4 into a sequence of length 3? Now, how do we get to this question? And frankly, it's not going to be the first question that comes to you, right? This is not the most obvious question that comes from this. But if you ask a bunch of questions, you're eventually going to arrive on that one. When you try sample inputs by hand of length 4, you're eventually going to be like, okay, can I simplify this down because it gets really complicated? Even some of the 3 ones are a little tricky. So eventually, you're going to get there if you just keep going. And you keep asking the questions, you keep solving a lot of different problems, so you are used to the types of questions you need to ask. And again, that's the key there. When you solve a lot of different questions, you want to be used to the types of questions you need to ask, right? You want to be used to this problem-solving skill of what questions do I ask to solve a problem. You don't want to be more and more used to what's the answer, because what's the answer is not going to repeat itself. What types of questions do I need to ask to get to the answer will repeat itself. Okay, so let's say that I had like these 3 here, and this one here is an R. How can I do this? Well, I can stamp it with like a BR, right? White by BR. And then I'll just do these 3 to be whatever these 3 is. And we know we can make anything other than RRR and BBB. And one thing you might notice is that obviously 4 R's is impossible, right? We already know that. And we know that all of these are possible. But is BBBR impossible? And the answer is no, because we can stamp BR here, and then we'll just stamp a BR here. This becomes B, this becomes R, and then we'll stamp BR here. Okay. Now the question is, are you starting to notice a pattern? Right, we did a bunch of different inputs. We asked questions so we can solve more inputs. And the pattern that I'm noticing is that, yes, we can't do all 4 letters. All letters are the same. But if there's even 1 letter different anywhere, we can do it. Okay, I notice this pattern. Can I prove this pattern to myself, right? That's the second part. Can I prove it? And honestly, for greedy problems, you're not going to always be able to prove it. So what you want to really try to do is, can I break this? As in, what makes this work and can I break this? For this problem, it's probably the easier grading one. So you can probably just prove this. And how I would prove this to myself is let's say I have an R somewhere and the rest are B's, right? Or let's say I have like some random sequence. These have like some random letters on it. And I want to make this one R and the rest of them B's. Well, I would just stamp RB here. And then, to get the rest of them B's, what I'm going to do is I'm just going to stamp like BR everywhere. and then BR here, and then BR is going to temp here, and then BR here, and then BR here, and then BR here. So I can get one R and the rest B's, and then to move this R over where I want it to move, well, I can just move the R by say, let's just say I stamp this one. I can make it RB. And then if I stamp this one, I can make this R and this a B, and this R and this a B. So I can move the R over. Similarly, I can create a second R and move it over. And so as long as they're not all the same letter, the answer is going to be yes. So what is the runtime of this? Well, we need to check if they're all the same letter. How can we do this? Well, we can just loop through the entire array, and we're going to ask two questions. Question number one, do I have a B? Question number two, do I have an R? Now recall that we're not considering the whites, right? We're solving every sequence of it differently. So in every single sequence, we're going to ask the question, do I have a B? Yes or no? And do I have an R? So let's just say the sequence has, X elements. Well, we can do a loop through once to say we do have a B. Second time, do I have an R? So in O of X time, we can check this out. We can solve one sequence. If we have multiple sequences, we have to loop through the entire array. And between the W's, we'll just do this check. Does each of these subsequences have a B or an R? So we can do this by looping through the entire array just one time, right? If we see W's, we just keep going. Once we stop seeing W's, now we're going to check. Does the second one have a B? The second one have an R? So the array has n elements. We have O of n runtime. And here, n is 10 to the power 5. This is O of 10 to the 5. Now, in this problem, we know that you might originally think that, hey, the answer is t times n. And t is 10 to the power 4, n is 10 to the power 5, so this is going to be 10 to the power 9. Or not 10 to the power 9. I'm going to send this equals 10 to the power 9. And 10 to the power 9, again, is too big, right? Remember we said last time, for C++, you can do 5 times 10 to the power 8. For Java and Python, you can do 10 to the power 8. But Python sometimes even lower than this. However, notice what it says in this line. It is guaranteed that the sum over of n over all test cases does not exceed 10 to the power 5. So this means instead of it being n times t or t times n, it's just going to be 10 to the power 5 instead. We can consider t times n over 10 to the power 5 because the sum of, like, the reason we multiply them together here is because we think for every t we can have 10 to the power 5. They're saying it's not true. They're saying in total it's 10 to the power 5. So if test case 1 might have, 10 to the power 5 minus 7, well, no, test case 2 can't be bigger than 7 of n. So in total, they're all going to sum up to 10 to the power 5. So this is going to be fast enough. And this is called amortization for runtime. It might be a little tricky, but all you need to know is sum of n overall test cases, right? So it's sort of like an n times t type term. Instead of, you can replace it with 10 to the power 5 because it's telling you that it's not going to be bigger than 10 to the power 5. So instead of using n times t, you can just replace it with this. Okay, so now let's write the code. First contains t, the number of test cases. This problem is a little more advanced than some of the previous ones, so I'm not going to go through the whole, make sure you're correct number of input, correct number of lines of output and input. I'm just going to go through the writing the code. Water real quick. All right, so we have n, the length of the picture. For each test case, so we're going to loop through all test cases. The reason I'm using test here instead of I is so that I can use I like inside the loop, but it doesn't really matter if you want to use I here. Okay, then we read an n, and then we read in the string. All right, so now we have n, which is the length of our string, and our string. And now we need to figure out if the output is yes or no. All right, so let's first have a variable for what our answer is going to be. We're trying to answer it as a yes. We're going to assume that nothing bad is happening. And again, every range needs to have an at least one R and at least one B. So if it ever doesn't, we're going to change our answer to no, but we're going to default as yes. And if we ever find something bad, we're going to say, hey, the answer is no. Okay, so now let's loop through the string. And we can use a for each loop here. What this will do is item will first equal the first item picture, the first character picture, the second character picture. So this is essentially the same thing as for int I equals 0, I less than n I plus plus, item equals picture of I. Okay, so there's a couple cases, right? First, let's just say if item equals W. What happens if we have a white letter? So whenever we see a white letter, instead of thinking of ranges, so the ranges is going to be between two whites, right? And so when we see a white, this could mean a couple things. First of all, it could mean that our range just ended, like it does right here, right? When we see this white, we see this white, a range just ended. Or it could mean that, like when we see this white, the previous one was also white. Or when we see, this white, when we see this white, there was nothing previously. So we want some concise way to do all these, because I don't want to do a bunch of if statements. I want to have like a short and concise code here. So what I'm going to say is, let's first think of what do we need to do with this sequence of R's and B's before it. Well, as we said, we need to check, does the sequence have an R? And does the sequence have a B? And all right, so we'll get to the okay, let's just move on from now for the W's. We'll get back to it. Here's a nice way to implement. So then we're going to say in the other case, we have R or W. Okay, how do we check if we've started a sequence? Well, we've started a sequence if, like here we see a sequence of R's and B's. There's two cases, right? We started a sequence if the previous one's a W, or if we're the first character. So there's going to be a trick I'm going to use here. What I'm going to do is I'm just going to add a W to the beginning of the sequence. Always. Just add a W to the beginning of the sequence. Why? Well, it doesn't change the answer. And now I have a cheat. What I can say is a sequence has to start after a W in all cases. So I'm just going to say picture equals W plus picture. Okay. So actually, let's just loop through all the characters here. Okay, and then we'll just add 1 to n, because now the length of the picture increases by 1. Why do I start I at 1? Well, the reason I'm going to start I at 1 here is because we know the first value is the W that we just added, so we don't really care about that. This is everything next. All right, so if we see an R, first thing we need to do is check, are we at the beginning of the sequence? We're at the beginning of a sequence if the previous one is a W, right? So just have char item equals picture of I, and char previous is going to be picture of I minus 1. Okay, so if the previous was a W and now we have an R, we're at the beginning of a sequence. So if we're at the beginning of a sequence, what do we want to do? Well, what we're going to do here is, now we need to check, does the sequence have an R, is the sequence have a B? So we need to have a variable for this. So bool has R, and the sequence start out as false, because we haven't seen any R's. And we're going to have the same thing for has B. Start as false. Actually, I'm going to make this a little more a little more concise. I'm going to say if the first one's a W, that's that. Else, the first thing we do is check if we're in the sequence. So if. So here, this could be an R or a W. We'll come to which one either. We're going to come to which one it is later. So it could be an R or B, sorry, not W. Okay, so previous is W. We're at the beginning of a sequence. Okay, so for our sequence, the first thing is we're going to say is, hey, for our sequence, we haven't seen a B and we haven't seen an R yet. And the current value is going to be an R. We're going to update that in a second. We're going to say, hey, currently new sequence, we're going to reset these two variables because the previous sequence could have set has B to true, right? We don't know. All right, so this is going to be reset our variables. All right, what do we do next? So now we know that we've seen the sequence, and what we're going to do is we're going to say, hey, if the current item is an R, well, then we're going to set has R to be true because this current one has an R. Else, if the current item is a B, I want to set has B to be true. Okay, so we've reset our variables, and then here we're going to update our variables. The current letter. Okay, so now if we've seen an R, when we're inside the sequence, we're updating if we have an R or we have an B. So at the beginning of the sequence, we reset everything, and then we update with the entire sequence. Cool. Now, the interesting thing about W is, like, in between these W's, there's a bunch of them. We don't really care. But what does matter is this first W, because this first W means that, hey, the previous sequence is over. Right? And if our previous sequence is over, then we have to check, hey, did the sequence have set both has R and it has B to be true? Did it? If not, our answer is false. If not, this was just all R's or all B's. So then we're going to check here. If previous is not a W, then this means the last sequence just ended. So if has R is false, right? And we can check if has R is false by saying if not has R. Or not has B. Then we're going to change our answer to no. Okay, so this takes care of the sequence that just ended. Now what we need to do is, there's one catch, right? We start off our variables but both false. And so the first thing we're going to put is a W, and then it's going to say, oh, these are both false, and the answer is no. So we're just going to initialize our variables to both be true and saying, hey, we're going to just pretend that any sequence that occurred before these W's, it was fine. And this should take care of it. So yeah, at the end of this loop, we will just output our answer. And let's try this out. All right. Okay, we have a little bit of a bug here. Oh, right. So there's one more issue, right? Here we only set the answer to no when we see a W. We assume that W is the end of our range. But what happens if the sequence just ends in a RBR? Then there's no W here, and then it's never going to reach this part of the code. So to fix that, we're just going to do a little cheat again, and we're going to add a W to the end. And we're going to add 2 to n instead of 1. All right, let's look at this. Yes, no, no, no. Yes, yes, yes. No, yes, no, yes, no. Perfect. All right, so let us submit this then. Awesome. All right, 4 down. And I'm just going to see if there's any questions real quick. Any comments? Nope, we're all good. Cool. All right, let's get to problem E. Problems are there. There are 4 problems left. All right. Given n strings, each of length 2, consisting of lowercase letters from A to K, output the number of pair of indices I and j such that I less than j, and the ith string and the jth string differ in exactly one position. My first thing here is when it says A to K before I even read on, how many letters is that? A, B, C, D, E, F, G, H, I, J, K. That's only 11 letters. So this suggests some like runtime, which has to do with the number of letters. Just interesting to think about. All right, let's keep going. In other words, count the number of pairs I and j such that the ith string and the jth string have exactly one position p. Oh, the strings are of length 2. Just that they're not equal. And you should use a long to avoid overflow. Okay, so it's quite interesting here. The strings are only 2 letters. And one letter has to be the same, and one letter has to be different. So you might find that this problem here is actually very similar to another used to code problem called compatibility, which is a gold problem. This is a lot easier version of that problem. So what does it mean that the 2 strings must differ in exactly one letter? This means that one of the letters must be the same, one of the letters must be different. So 2 strings can't be identical. Now, an interesting note here that I will make. So the first strategy, right, is noticing the problem solving strategy here I'm going to give you is notice small constraints. Oddly small constraints. In this case, there are only 10 letters or 11 letters. Someone asked you a question. How many unique strings are there that they can possibly be? Well, the answer is there's only 121 possible strings. Because each string is 2 letters. And we have 11 letters. So there's only 121 possible strings. What does this mean? It means we can literally brute force all possible pairs of strings. So how many pairs of strings, right? There's 121 squared possible pairs of strings. And we can approximate this to 100 squared to the power 4. Was this the problem where, okay, let's see. E is less than F. All right. So, it's just one of those things where, like, if you don't think twice about the fact that it's A to K, right? It's oddly small. Because this could be Z, A to Z. It really could be. And it's not. So the question is why? Why is this a small constraint? If you don't use the fact that it's a small constraint, for hard problems, you're almost certainly not going to get the answer. And then this problem, as soon as you notice the oddly small constraint and you try to ask yourself why, just try to figure out why, try to figure out what is this limit, try to figure out what's not possible, what is possible. And first all possible pairs of strings. And you'll notice that some pairs, like they have to, since we have n string to n is into power 5, we have to definitely have some strings that are going to show up multiple times. If a string shows up multiple times, let's add value to the answer the same number of times. Right? So kind of like, where do we go from here? When we brute force all possible pairs of strings, we figure out that, say, like AC and AB are valid. And let's say that AC occurs 10 times, say 9 times. And AB occurs 5 times. What do we get to answer? This goes back to the previous problem, the problem solving strategy of asking ourselves questions. So ask yourself this. AC and AB are valid. AC occurs 9 times. AB occurs 5 times. What do we get to answer? And if you can't figure this out, then hey, reduce the number down to 2 and 3 and try solving it by hand. Because you can solve this by hand. Right? And you will figure out that what you have to answer in this case is 6. Then maybe like bump this up, right? AC occurs 4 times, occurs say 4 times, and solve it by hand. 16. Okay. Now go back to AC occurs 9 times, and this occurs 5 times, and you'd be like, yeah, we're multiplying them together. This is 45. And that's what your problem solving strategy is going to want to look like for this problem here. All right, cool. So we have that. And yeah, so then we'll just okay, so then we need to count the number of times every string occurs. And I'm kind of just working through different parts of a problem here, right? I'm trying to say like these are the observations I make. It sort of seems like it's possible to brute force. How would I solve this part of the problem? And the next question is, how do I solve the part of the problem where how do I count how many times each string occurs? And here you can use a map for C++ or something similar called the dictionary in Python. It's also called a map. I think it's called like a tree map or a hash map. And you can also use a map slash map in Java. All right, so now we need to put all these things together and get our code working, right? And again, these two questions came from like, what do I have so far? And with this is not a whole solution, right? This is something which came from all these small constraints. What more do I need to solve the problem? And that's where these two questions came out from. It came out from what am I missing in what I have so far? Okay, so let's just go through it. We have a value of t. And we have n. And we have our strings. Now, I'm just going to put a map to count the different strings. So we'll create the map here. So let's loop through all the input strings and we're just going to add them to the map. So for every string that occurs, we're going to count the number of times it occurs. So we first check if it's currently okay. If the string is currently in the map, that will come to the loop. String is currently in the map. Then we're simply going to say count of temp plus plus. Else we're going to add it and say it occurs once because we saw once. Cool. So now we know how many times each string occurs. The next thing to do is we need to answer the this is basically with the input. We need to answer the problem, right? How many times do or how many of these pairs do exist? So I'm going to do something because it's going to use long. So I'm going to say define int is for long. So all my ints will be longs here. I'll just move in from int main so that all my ints will be longs. So essentially mean I don't have to type long everywhere. Okay. So I want to point out that there's only 10 to the 4 possible pairs of strings. And these possible pairs of strings do not change between test cases. They just don't. So I can pre-compute for all the possible pairs of strings. I can pre-compute them outside the for loop. I can pre-compute them here. But the thing is, there's nothing really to pre-compute. Because the thing is, if you give me like two strings like A, B, and AC, I know the sorry, I hit my mic, but I know that they have one letter in common. And it's obvious. A is just A in common. So there's nothing really to pre-compute in the sense that once we have this count, right? Once we have how many, if I count how many strings occurs, then from there we can start going directly to our answer. We can loop through all possible pairs of strings, and we can just do this multiplication to figure out what to add to our answer. So I'll show you what I mean here. Let's say int answer equals 0. So we need to loop through all possible pairs of strings. Now I'm just going to Google real quick to see if there's a quick way to get all of the keys in a map. I believe actually, okay, I'm just going to try this. And again, if you don't know the syntax or anything, you can always look it up. String key 1 in count I'm just going to say C out key 1. Just to make sure everything's working real quick before I keep going. I just want to make sure that I have the syntax down correctly. Ooh, I guess I do not. You know what I can do? I can do this. I can have a map string int iterator, and I can say for it equals count.begin. It is not equal to count.end. It plus plus. This will iterate through the map, and I can say cout star it. I just want to see if this is going to print the key or the value. It's also not working. Let's see. All right, I'm just going to Google this real quick. Okay, so this is how we want to do it, seems like. Oh, I guess we'll just, this compiler may not be accepting of this. We'll just do it later. Okay, perfect. So it is printing out all the different items in all the different keys that we have. Now, the thing is, I want to make sure that, because I want to loop through every pair of them, right? And I don't want to duplicate any pairs, obviously. So what I'm going to do is I'm going to create a vector. And this is going to be all the different strings that occur. So here I'm going to say diff strings dot pushback. Okay, cool. This seems to work. So what we're going to do from here is, int m equals diff strings dot size, could be length, I'm not sure. If it's length, we'll just fix it later. For int I equals 0, I less than m, I plus plus. And then for int j equals I plus 1, j is less than m, j plus plus. This will loop through all pairs of strings, right? So string 1 is going to be diff strings I. String 2 is going to be diff strings j. So now we have the two strings that we're looking at, and now we want to check if they have one letter in common. So if this is for every pair, right? So we have our pair of strings, right? AC and AB. We need to check if they're valid. Okay, so we're going to know they're not the same string, because if they were the same string, then I would equal j. We started j at I plus 1. So they're not the same string. So we just need to check if either the 0th character is equal or the first character is equal. Then they have one letter in common. All right, what do we do if they have one letter in common? Then we're going to add to our answer. What are we going to add to our answer? Well, we're going to say AB occurs 9 times, ABC occurs 5 times when we add the product of the two, right? So we're going to add count string 1 times count string 2. And yeah, what we're gonna do here is I'm just gonna put define it long later, so that should take care of. Actually, I'm just not gonna define it long. Too complicated. Let's just take care of this here. We're gonna make this a long answer. And I'm just gonna map a string to a long. And the reason we're gonna mapping a string to a long instead of an int is because if these two are both ints, then the product is also going to be an int, and that will overflow. So these two need to be long so that the product is also a long and this doesn't overflow. All right, at the end, we're going to see our answer. And takes care of that. Okay, so we have the input already in. Let's run this. 5606, perfect. Before we submit. Okay, there we go. Okay, it also works. Awesome. Let's make sure there's no questions. Perfect. Cool. 3 problems left. Let's see. Eating candies. There are n candies put from left to right on a table. The candies are numbered from left to right. The ith candy has weight WI. Alice and Bob eat candies. Alice can eat any number of candies from the left. She can't skip candies. Bob can eat any candies from the right. He can't skip candies either. Of course, if Alice and Bob cannot eat the same candy, perfect. They want to be fair. The total is to eat the same total weight of candies. What's the most number of candies they can eat in total? Okay, so in this question, let's move our code. Let's take one of the samples here. Seems like a good sample. All right, so what are the different numbers that Alice can eat? Well, she can have 7, 10, 30, 35, 50, 51, 62, 70, and 80. Oh, what am I doing here, by the way? Just for the problem solving strategy, because I want to be clear about that. What I'm doing is I'm solving a bunch of sample inputs by hand. And the one that they have happens to be a good one to do by hand. So I'm doing that. Okay, Bob, and he starts from the right side. So I'm just going to write it with a pen. He can have 10 or 18 or 29 or 30 or 45 or 50 or 70 or 73 or 80. And by the way, like the number in this location, 70 is how much Bob has if he eats the candy, 30 is how much Alice has if she eats the candy. Okay, so now if I want to maximize them, clearly what I am going to do is I'm going to give, well, I can't just give 50 to Bob and 50 to Alice because then 2 of these candies are overlapping. That would be my first preference, but that's clearly not happening. What else could I do here? All right, what is the answer? I guess let's look at that. The maximum that I can eat is 7. Okay. What did they ended up doing for the last case? Alice eats the first 3, Bob eats the last. Ah, okay, I see it. So Alice eats this, and Bob eats this. Now, for those of you who know what prefix sums are, you can clearly see that I wrote out the prefix sums for Alice here and Bob like backwards, so it's technically suffix sums there. And this was kind of like the intuitive thing to do. Unfortunately, the reality is if you don't know prefix sums, you are not going to be able to get this problem. Maybe you could figure out prefix sums in contest and learn it in contest, but the idea simply is the same, that like if you haven't taken the time to prepare and learn prefix sums before the contest, you're unlikely to get this problem. And this is where preparation definitely comes in handy, like of learning different algorithms. The first few problems were all different problem solving strategies that you need to learn. Here is just straightforward algorithms. You need to know prefix sums in order to have a chance to solve this problem. Okay, but from prefix sums, what do we do next, right? Because clearly we can't just test all possible values that Alice has and all possible values that Bob has, because this will take n squared, and n is 10 to the power of 5. We can't do n squared for that. So what we kind of want to do is we want to be able to say something a lot simpler. What if we just be able to ask them, like, let's go back to the problem solving strategy, because it's not just prefix sums, right? There's clearly more than that. If you want a good prefix sum problem, breed counting from skill silver is a good prefix sum intro problem. This is just prefix sums, but they don't have those anymore. This one here, it's a lot more to it. So, what you might the problem solving strategy, that's what we're at. Okay, so the problem solving strategy you want to be able to use is going to be asking questions. So the question that, again, try a bunch. The question that you might end up with is, let's say Alice chooses to take 30. Is it possible for Bob to match this and also take 30? Essentially, is there a 30 in this range here? And the answer is yes. So we have, this works. If the question was, is it possible for Alice to take 35? As in, is there a 35 in this range here? The answer is no, so it's not going to work. Okay, so that's essentially the idea behind this problem. Now, again, if you've not seen prefix sums, you have no chance of getting this. Similarly, if you've not seen sort and sweep idea before, you have no chance of getting this problem either. Because, let's just see if I can get the text back. No, the text that I wrote was gone. All right, let's draw this back. 10, 15. Okay, so in order to be able to ask the question like, hey, if Alice takes 30, is there a 30 in this range, right? And we're gonna ask that for like all of Alice's values. That's just the simplest way to approach this. So again, if you've not seen like the sort and sweep idea, you have no chance of getting this problem. And I'm not going to teach any algorithms in this video. That's not what the point of this video. So if you've not seen prefix sums or sort and sweep problems before, go learn those and then come back here. And also, you know, sets. If you've not seen sets and multi-sets, go learn those and then come back to this video later. Because, like, if you've not done those before, you're just not going to get this problem, which is unfortunate. But again, you learn these topics once, you can reuse them over and over and over and over again. That's not that bad, right? And then once you do, it puts you at an advantage to everyone else who has not learned these topics. It's actually a benefit in that way if you think about it, right? Just learn these a couple times, or learn these once actually, and then you're at an advantage to everyone else. Now, on the other hand, I'll just go into this, I'm talking about already. If you waste your time learning algorithms that don't show up often, then you're at a disadvantage to everyone else because you spent all that time and you're just not, like, it's not useful. All right. So okay. So how are we going to do this for an sweep idea? Well, we want to be able to loop through each one of Alice's values and ask, hey, does Bob have that? And, you know, when Alice moves from 30 to like 35 here, and then Bob's range shrinks, sure, you know, we can make a Bob array start out with all the values and then delete the values one by one. So here we would just, if we put all of Bob's values in a set, we would then say, hey, we can just delete this, and now we can query Bob's set here to see does 35 exist in it. We'll find that the answer is no. Another way to do this in equally valid way, this is the way that I'm probably going to end up implementing. Actually, I'm probably implementing this deletion method. But another equally valid way, if you don't want to do deletion, if you only want to do insertion, is what you could do is you could say that Bob's range, let me delete that one, 0. Okay, is you could do Alice's range is going to start out from here, and then we just look at Bob's nothing, and then we see, okay, Alice has 70, and then we just have to insert 10 into Bob's set, and say if Alice makes 62, and then we insert 18 into Bob's set, and so on and so forth. As I said, I'm probably going to end up doing the deletion method, where we say, hey, Alice has 30, is 30 in Bob's set, and then, if Alice has 35, is 35 in Bob's new set. So I'm probably going to end up implementing this method, but both are equally valid. Okay. What's the runtime of this? Well, we're doing a sweep, and for every time we do the sweep, we're going to remove one element from the set, which is log n. So for every element in the array, so n elements in the array times one deletion from a set is going to be n log n. So runtime is going to be O of n log n, and looking at this is we have t test cases, so it's going to be t times n log n. However, the sum of n over all test cases then is 2 times 10 to the power 5. So we can think of that as 2 to the power times 10 to the power 5 times log of that, which is perfectly valid. And the reason I think I explained this for an earlier problem today, so you can just go back and watch. I think it was problem C or something. All right. Let's get into implementing this. And there's a lot of details that people have when they implement sort and sweep that can really make a difference in your code having bugs or not. So I'm going to walk through all the details here that we do with sort and sweep to make sure that it works out. And the thing is, like, these details are very, very simple, and there are very few of them. But if you just get them right, then codes work a lot more often and without bugs. And again, your code's right either way, but it's just an implementation details to reduce the number of bugs and help your code be smoother, and you write your code faster. So let's read an n. Now let's read an R array. Now we have to go through that process where we add all of Bob's items. Oh, we have, okay. So we're gonna make our Alice array, which is the prefix sum, and our Bob array, which is gonna be the suffix sum. So Alice of 0 is gonna equal to W0. And then for int I equals 1, is less than n. So Alice is the prefix, and then Bob is going to be the suffix. So for the suffix, we're going to start out at Bob of n minus 1. Okay, so we have our prefix and our suffixes. So now we're going to add up all Bob's values to a set. Actually, a multi-set, because we could have duplicates, right? Oh, Wi can't be 0. Okay, so we can't have duplicates, so a set is fine. And we're going to initialize it with all of Bob's elements. Actually, we know that. I'm just going to paste Bob's values in here, because we know it ends in 80, so working backwards isn't that bad. 3 minus 5 is 48. Okay, I think I messed this up. 80 minus 7, minus 3 gives us 70. Then minus 20 is 50. Then minus 5 is 45. Then minus 15 is 30. Then minus 1 is 29. But 0 doesn't actually exist in our array. Okay, so Bob has these values and Alice has these values. Perfect. So one thing that when we start off, right? When we start off, we're going to look at, like, it's going to be impossible for Alice to take the last value in the array. Why? Because then Bob is going to have nothing and he's going to have 0. So when we start off with Alice taking the first value, we're going to have Bob taking everything but Bob of 0. Like, it's going to be Bob of 1 through Bob of n minus 1. So when we start off with the Bob's array, we're going to make sure we don't include the first value for Bob values. Y. Perfect. And then we're going to do our sweep. So let's loop through all of Alice's values. Okay, so here's the key principle when doing a sweep. That's going to make your code just go so much smoothly. Step 1 inside your loop is going to be update your answer with your current data structure. And then step 2 is going to be update your data structure and current value. It's going to be update your data structure with your current value. Why is it important that you don't switch these two? Because whenever I see people switching these two, it's like your current value sometimes doesn't need to update your data structure, and it just messes up with your answer. Even when I see people do centroid decomposition, there were several bugs in USUCO camp. Centroid decomposition, you don't know what that is, but it involves a sweep. There were several bugs in USUCO camp that people had, not in their code necessarily, because I haven't seen their codes, but when discussing the algorithm, I noticed that several things people had could be solved by doing stuff in step 1 and 2. And because we're very unclear about the order, that they can maybe do this first and then this, then you can get things muddled, right? And so if for all your sort and sweep problems, you're able to keep this structure, you will keep things very clear. And in this problem, you could do things in the reverse order and it won't harm you at all. But if you keep the structure for a bunch of other sort and sweep problems, like if you take this and go back other problems you solved, you're going to notice that if you did do it in the reverse order, you have to do a lot of other random steps to try to get it to work, and a lot of other random code. So make sure to always do sort and sweep in this order. Okay, step 1 is update our answer. Whenever start initialize our answer, right? So let's initialize our answer to be 0. And so update our answer. So how do we update our answer? Well, if we have a value like 30, we have to see if Bob values also contains 30. So if Bob values dot find, what is the value that we're looking for? Well, we are looking for Alice of I. This is not equal to Bob values dot end. And this is just doing, it's basically saying, this basically just checks if Alice dot I is in Bob values. All right, what do we do in this case? Well, then we can update our answer. Max of whatever the current answer is. And Alice of I. Perfect. What do we do next? Update our data structure with the current value. So now we have to say, okay, we originally had this and this. So now we need to remove 50 so that next time we only have these values. Of I plus 1, I believe. And we can just end at n of I n minus 1, because it's going to be impossible for Alice to take the last value, because then Bob will have a 0. Actually, earlier I remember saying, I just said that this problem doesn't really matter if you do it in reverse order. You'd have to structure things a little bit differently. Like Bob would start with all the values and you just remove the ith value or something. So it would be just fine for this problem specifically, but I again want to reiterate, for a bunch of other problems, it's not going to be fine. So make sure you do it in the step 1 and step 2 order. Okay, so at the end, what do? We just print our answer. Oh, it's not remove. I think it might be erase. Okay. This is printing out the what we set it to, which is Alice of I. What we actually meant, when we actually wanted it to print out instead, I made a mistake here, was the number of candies, not the sum of the weights of the candies. So what is the number of candies? Well, in this case, Alice has I candies, and how many candies does Bob have? Well, how many candies Bob has depends on the index, right? So when Alice is at 30, Bob's 30 means he has 4 candies. So we're actually not storing how many candies Bob has inside this data structure. And so we need to do that. So instead of just storing the number of candies that Bob has, we're going to store a pair, which is going to be the number of, the sum of the weights weights of candies and the number of candies. Actually, wait, I have a better idea for this. So Bob values, I'm just gonna put a comment about this. This is gonna be sum of weights of candies. And then we're gonna have a map, which is gonna map, is gonna, let's call it num candies. So it's gonna have, so num candies of sum of weight of Bob's candies is gonna equal to the number of Bob's candies. So here we say Bob values and insert Bob of I, and we're gonna have num candies, Bob of I, equals the number of candies that you're gonna eat. And so if, let's like calculate this out because we'll make sure we don't make any errors. But essentially the idea is pretty straightforward, right? If we're at n minus 1 here, then we're gonna want 1 candy. If we're at n minus 2, then Bob's gonna have eaten 2 candies. And again, n minus 3, then Bob's gonna have eaten 3 candies. So I'm just going to do n minus I, right? And this is going to essentially be your value I. I'm going to do n minus I, and that's going to be the number of candies. All right, so how many candies? Well, Alice is going to have eaten I plus 1 candies, because if it's index 0, Alex has eaten 1 candy. Plus Bob, well, we know how many candies Bob eating, because we're going to have that num candies. And Alice of I equals the number of candies Bob's eaten too. So we can just put an Alice of I there. We do not need to erase num candies because we just won't use it. Like once it's removed from Bob values, we're just not gonna ever refer to that in number of candies. So we're fine. Okay, if we run this now, 2607. Perfect. This matches our answer. So let's submit this. Oh no. All right, let's take a look at this. All right, I'm going to suspect that the issue probably lies in, the issue probably lies in using ints versus longs. Let's just think about this. Well, no, so the max number of candies they can eat is going to be the weight just 10 to the power 4 times 2 times 10 to the power 5, which is small enough that it should that's just 2 times 10 to the power 9, so I should put in an int. Let's make sure that we reset these variables every single time. So we're reading all of these W values. Yep, Alice I equals, Bob I equals. All right, I guess let's just try a couple test cases then and try to get something to work. Or something to fail, technically. So we want to find, so here's our debugging strategy. And this is a good time to go over it, even though it's unfortunate that the code's broken. We're going to try a bunch of test cases and try to see if we can find one that breaks the code. So let's try something where we have, say, 4. 1, 2, 3, 4. This should output 0. Okay. What if we have now 1, 1, 1, 1, 4, which is correct. Okay, let's say we have 1, 1, 2, 1. And the reason I'm trying these is I'm trying test cases which are edge cases. So I'm trying where we have duplicate values because that's where we make up. Okay, so here also says 4, which is correct. 2 and 2. What if we have 3? This should say 5 now. It does. Interesting. code real quick. Because we are using like n-1s and 1s and n-1s and stuff, it might be also worth having a test case 2, just with 1 is going to give us 0 as our output. So let's try 2. Okay, this seems to work. All right, let's just do a big test case then. All right, this should give us 10. It does. But if this is a 3, 0, let's see. Actually, I didn't calculate beforehand, so let's see if this is valid. So let's find something a little easier, maybe. Make this 11. Make this a 4 and 3 at the beginning. Interesting. So what is the one that's failed on? Out of bounds error. Did I make them? Oh, W is up to 10 to the power 4, but N is up to 2 times 10 to the power 5. So this is an out of bounds error. They're completely right. Let's try just fixing that. Perfect. All right, 2 more problems left to go. See any questions? Nope. There is a grid with n rows and m columns. There are 3 types of cells: empty cell denoted with a dot, stone with a star, and obstacle with the letter O. All stones fall down until they meet the floor, which is the bottom row, an obstacle, or another stone which is already immovable. Okay, simulate the process. What does the resulting grid look like? So here, I guess the first thing to know in things falling down is that when you're simulating said process, right? It's just some general intuition. Let's say that we have like empty star object, empty star object. If we simulate this object falling down first, it comes here. We simulate this object falling down. Wait, now this one has space to fall down. So that's going to be really annoying. However, if we simulate the bottom one first, then this one comes down here, then this one comes down here, then that works out. So that's the first key that works out. Oh, I think stars are the objects, not the O's. O's are obstacles, but same idea, just for stars instead of O's. And where do you get the intuition from? That intuition comes from solving problems with grids that which have stuff that fall before. And if you have not done that, this is all impossible to get this problem without having done that. It's just annoying because you have to try out several different test cases. You try to algorithm on several different inputs, and you eventually find out that this is the most efficient way to do it. But you can definitely get this by solving several inputs by hand. All right. Anything else that we need to know? Well, the other observation that you might make here when you solve a bunch of inputs by hand, and again, solve a bunch of inputs by hand to come up with these observations yourself. But the second one is that, if you have items on one row, they don't affect the other row. Essentially, each row is its own individual problem. So we solve each row separately. And each row we start from the bottom, go to the top, and just push the items downwards. And so, yeah, it's just pretty straightforward like that. The question now becomes, how are we going to push the items downwards? So let's go into detail of that, right? Let's take, let's try this up. Let's take this right here and say, how are we going to push the items down? So we know we first have to move this item down, right? Because if we move this item down first, there's like no place to move. But then once this one moves, this one has space, and it's just annoying. So we're going to move this item here. So now this becomes a star, and this becomes a dot. Now we have to move this item. So the easiest way to move this is to loop through the entire row and find the lowest spot that's available and just move it. That's essentially all we're going to do. It's just an implementation and simulation problem. Now, the trick with implementation and simulation problems is to keep your code neat and tidy. I imagine that a lot of codes for this problem are going to be like 200 plus lines. It's just way too over the top. You can get them to work, but they're just gonna have to be a lot more buggy and weird. Not weird, but like a lot more buggy, I guess, is the best term to describe it. So if you keep your implementation short, how do we do that? By having a clear, concise structure for our code. So let's get into that. Where we have T and M. All right. So again, we're just gonna keep everything super straightforward, and we're gonna do everything we're trying to do one by one. So every test case is obviously the easy part. Now we're gonna solve every row simply, or sorry, every column separately. What am I to say? So let's leap through every single column. Okay, and now we want to solve every cell in the row from bottom to top. And I'm going to call this a row because we're looping through the rows, right? We have our column. We know we're doing the second column or whatnot. Let's draw this out. We know we're doing, say, the second column, and now we just need to know what row the cell that we're looking on is. Maybe it's this row, maybe it's like this row, maybe it's this row. So we're going to call it row. And we're doing n-1 down to 0 because we're going to start out with the bottom row and go up the top row. Okay, so now our cell is row call. Oh yeah, and we need our grid. So N and M are 50, so it's 50 by 50 character grid. And we should just read in our input first. Here's to make it convenient to use variable test, because then you can use I and J here. But again, J and K is not the end of the world either. Okay, so you're reading our input grid. So now our cell is grid row call. And we need to fall. So we need to figure out, hey, where is it going to fall to? Okay, so first of all, we need to figure out if it's falling, right? If it's an O, it's not going to fall. So if grid row call, if it's an O, it's not going to fall. If it's a star, or sorry, a dot, it's also not going to fall. It's only falling if it's a star. So if it's not equal to a star, then what I'm going to do is I'm going to use a command called pass. Sorry, continue. And what continue does is it says it's going to skip everything else inside the for loop. So it's going to go back to it's going to go to the next iteration of this for loop. It's going to go to the next cell. All right, so otherwise it's star. So we need the star to fall. So we need to figure out where it's falling to. So we're just going to loop downwards and figure out the first thing that's full. This is going to be N. Okay. So if grid row 2 call is not equal to an empty dot, well, then it's full, right? And let's just say int fall 2. So originally we're going to assume that we're falling to the bottom. And my phone is falling to the bottom. But if we find that, hey, there is a cell which is not an empty cell somewhere else, then we're going to fall there. So then fall 2 is going to equal to row 2 plus 1. And we're going to break. We're done with this. Nothing more to do. We figure out where we're falling to. Now, note that if the cell right beneath the current cell is full, for example, if we are, let's say we had a star here. If we're this star, and the cell right beneath it is full, then fall 2 is going to equal the current cell it's already at. That's fine. This means it won't move. Okay, so now let's actually make the fall happen. So grid row call is we're gonna make it empty, and then grid fall 2 call is gonna be star. And if fall 2 is the same as the current grid cell, then we're just gonna set it back to what it was. We set it to a dot and then back to a star, which doesn't really matter. Cool. So now the fall happened. The fall happened. Then we're essentially done. So we loop through every single column. Everything fell. We're done. We're good to go. All right. Then we need to output our grid. So let us output. So outputs our grid. You do not need to output a new line after each test. You know what? I think I'm just gonna put a new line after each test. Because it'll make it easier to read my output too. Just ran the code, and we're verifying that this matches. It does not seem to match. Hold on a second. It seemed to have deleted some stars. So let's try to figure out why. Second case seems to work. First case is not. Okay, so let's give it a simpler test case so we can isolate the issue of deleting stars. I believe this might catch it. Just make sure. Yeah, okay. Here it so it deletes this top star. So we're going to use this test case here to debug the code. Okay. So it's not a star, continue. Let's just make sure this is doing the correct function. Cout at cell row call. At cell, so we're at 1 0 first, and then we're at 0 1. So that is correct. Cout falling 2, fall 2, call. Okay, so 1 0 is falling to 0. 0 0 is falling to 2 0. This doesn't seem. Oh, this should be row 2 minus 1, not row 2 plus 1. Okay, this is correct now. Looks correct. Let us make sure it's not printing weird stuff. Cool. And let's get the original test case back in there. And it's minus 1 because the row above it is row 2 minus 1. And the row below it is row 2 plus 1. Okay, so this, yep, these all seem to match. Let's submit the code. Perfect. And last problem of this contest. I think I just checked the chat. Yep. Be sure to put questions in there if you like, but also if not, that's cool too. Actually, I do like questions, so if you have questions, put them in the chat. All right, well, and denote the bitwise AND operation or not bitwise OR operation. You're given an array A of length n, non-negative integer k. You can perform at most k operations of the given type. Select an index I or replace AI with AI or 2 to the power j. In other words, you can choose an index I and set the j at the bit to 1. Okay, yeah, so here essentially the idea is if you are not innately familiar with the and or operations, and I don't mean like the double and like this, right? Or double or. What I mean is like if I say A and B, like just two integers, right? Do a single and or a single or. If you're not familiar with these two operations, you should learn them right now. Oops. You should learn them, read up on them and learn them because yeah, you have no chance of solving this problem in contest unless you can figure these two out. That being said, you could probably figure these two out in contest. I have done similar things before. Obviously, it's a lot better to know beforehand. So right now, it's after contest. Go check those out and learn all about them because we're not going to go over the tutorial about how those operations work here. So we're only going to go over the problem. So it says output the maximal value of A1 and A2 and all the way to AN after performing at most K operations. Okay. So the j bit is up to 30. So if you know how sort of and operations work, what essentially happens is if we have a bunch of bits, like let's say the value we have in binary looks something like 0, 0, 1, 0, 1. And let's just say that j is like up to 5 for simplicity's sake, so we only have 5 bits. And we and this with like 0, 1, 1, 0, 0. If any bit, oops, it's a grid line. If any bit in any of the numbers, so let's even add one more number, 0, 0, 1, 1, 0. Okay, if any bit in any of these numbers is a 0, the end is going to be a 0. Any of these is a 0, which they are, so it's a 0. And this is a 1, 0, 0. Any bit is a 0, it's going to be a 0. And another thing you might know about these is that each of these is worth, the ith bit is going to be worth 2 to the power I, right? And that's interesting because if this bit changes from a 0 to a 1, that's literally worth more than all of the bits after we're changing all together. And this is because 2 to the power I plus 1 is greater than 2 to the power I plus 2 to the power I minus 1 plus 2 to the power I minus 2, and so on and so forth. So you got all the way out to 2 to the power 0. In fact, this is like 1 greater than this quantity here. And these are just math properties that like you just need to know. If you don't know, you may be able to figure them in contest. I'm not sure. But if I didn't specifically ever study math, I never made Amy. The reason I know these is from doing a bunch of bit operations from other UC problems. So this is a good problem for you to get started on working on bit operations for, right? Don't like run away because it was too hard. If this was within your 2 problems after what we were able to solve in contest, like your 2 up-solving problems, don't run away from it. Use this problem as an opportunity to learn about bits. Okay, so what does this property mean? It means my number 1 priority is I want to set the leftmost bit to a 1. That is my number 1 priority. Do whatever I can to set the leftmost bit to a 1. If I cannot do that, or once I do that, then my number 2 priority is going to be set this bit to a 1, regardless of what happened here. And then so on and so forth. So this creates a simple greedy algorithm. We're going to loop through all our bits from, I guess we're going to first start out by like just listing all these out and ending everything, right? Actually, we don't have to end everything either. But we loop through all our bits from left to right. Now we have k operations. And we're going to try to greedily set each of these bits that's not already a 1 to a 1. So how many operations does it take to set this first bit to a 1? Well, as we can see, there's 3 zeros that need to be changed to a 1. So it'll take us 3. With 3 operations, we can set this first bit to a 1. It's the first priority. With 2 operations, we can set the second bit to a 1. We need 0 to the third bit to a 1 because it's already a 1. And we need 2 here because there's 2 1s that are left. And we need 2 here. So you might start to see a little bit of a pattern here. What we're essentially doing is for every column, we're adding how many 1s we have. And n minus the number of 1s we have is the value that we need in order to set that bit to a 1. And the number of bits we have is 30. or sorry, 31, because 0 is a separate bit. So we have 31 bits. Okay, not bad, right? We can loop through 30 columns, and for every column, we can try to set it to a 1. We can calculate how many you set 1 and just greedily do it. And that's pretty straightforward, like what my thought process is and what your logarithm is, right? So thought process is sort of like, hey, given the problem solving strategy here is try a bunch of test cases. So trying this test case here gave us essentially all the ideas we need. You might need more if you're less familiar with this type of stuff. That's perfectly fine. Just do however many you need to get it. If you get a problem in contest, that's so much better than not getting it. So don't worry about how much effort it took you to get it. I mean, obviously it matters how much effort it took you to get it, but you got the problem, and that's just so much more important. All right, so we have our algorithm here, and let's just implement it now. It's our last problem. So we have our value of t, c and t, and then we have n and k. All right, so now let's just loop from the 30th bit down to the first bit. I like to use j for my bits. I don't know why. It's just a habit I've been doing since forever. So now notice this is 31 bits, right? 30 to 0 inclusive is 31. This works out. Okay. So we have our bits, and now we need to see, we need to count how many operations to turn this bit into a 1. And obviously, we'll start with having our answer, which is equal to 0. And we'll start just setting bits in our answer to 1 as we're able to do so. Okay, so int operations, we'll say 0 originally, and then we'll just loop through all our values. And if the value if it's a 0, we add 1 to the number of operations needed. For int I equals 0 as less than n. Okay, how do we check if a bit has a 0 in a particular location? What I'm going to do is I'm going to say if, we need to read in our entire arrays of a of n. And max in here is 2 times 10 to the power 5. Okay, so we say if a of I and 1 left shift j is greater than 0. What does this do? Well, what this does is, let's just say the number a of I is like 1 0 1 0 0. And j, let's just say, is 2. Or yeah, which is like this bit here. Okay, so 1 left shift j is going to be 1 shifted over 2 times. So 1 starts here, shifts over here. So that'll give us this value here. And when we end it with a of I, we get 0 0 1 0 0, which is greater than 0. So there is a 1 in a of I. Now, if this bit here would have been a 0, then when we ended it, we would have gotten a 0. So it would not be greater than 0. So then it wouldn't be 0. So if this is greater than 0, then there is a 1. So if it's equal to 0, then we need to do operations plus. Add 1 to the number of operations we need in order to turn this bit into a 1. Okay. So now we know the number of operations we need. We need to say, hey, is it possible to turn this bit into a 1? And that's if we have enough operations left. So if the number of operations needed is less than or equal to k, then we can turn the bit into a 1. Cool. So we'll just do that. We'll say k minus equal to operations. We will spend that many operations. And then we will say answer plus equals 1 left shift j. We will just set the bit to a 1 and add it to answer. And that's about it. Just print out answer at the end. Cool. Let's run this on the sample input. I don't believe we need longs here, just based on the fact that everything's less than 2 to the power 32. Oh, there's just a random D hanging out. Oh, looks like we need. Okay. All right, this is not right. So let's just try debugging it on the first test case. So it's just this one here. Okay. So the values are 2, 1, and 1. So let us say which bits can we, let's print out, can change, or can set to 1. Because sometimes we don't even have to change it. The and may already have it, in which case operation will just be 0, right? So can set to 1, J. Let's see if it's setting any bits to 1. No, so it's not trying to set any bits to 1. All right, so let's count the number of print out number of operations needed. So yeah, let me explain to you what I'm doing to debug when I have a test case that fails. What I'm doing is I'm sort of binary searching on the location of the bug. So first I'm saying, hey, what about here? So no, this is not reaching this print statement, meaning that this statement is wrong, meaning that the bug is somewhere up here. So now I'm printing here more. I'm printing more info here about the variables up here, so that I know which variable is off, so I can further debug. So I can print here operations needed for J equals operations. All right, well, for 0, this isn't correct, right? Because 2 to the power 0 equals 1, and this should have these two, and then for 2, it's also not correct. Okay, for 1, it's also not correct, because this 2 is 2 to the power 1. So something's going wrong here. What I'm going to do is I'm going to temporarily change this to only the values of J that are useful for us. So for 1 and 0, so that I have less random print statements, and I'm going to add more prints to this because operations is clearly incorrect. So I'm going to try to figure out why operations isn't getting updated. Sorry, why it's always adding 1 to it, why it's always 0. So let's see. I'm not reading in the input for A of I. That's so silly of me. And I figured this out by saying, okay, I was going to print I of A of I and 1 less than J, and then this and statement, right? That's what I was going to print right here. And then I realized I'm not reading in A of I because I know the issue has to come from either this or this. So that helped me debug, even though it was a very silly bug for me to have. Silly bugs happen, I suppose. All right, let's just say this fixes it. Oh, why am I making so many silly mistakes right now? Okay, 2, that is correct. That's correct. So now I can comment out my print statements. And I can go back to the original for loop. And the reason I'm just commenting them out and not fully deleting is because there could be a bug later, and it's just so annoying to have to re-add the print statements later. All right, now all of these values are matching. Awesome. Cool. So this ends this stream. We got all 8 problems. I hope this helps. And again, be sure to upsolve 2 problems from what you did in contest, right? So if you solved up to say like E, then solve F and G. In this problem, you want to switch the order of F and E for the upsolving just because the number of solves here are not sorted. Actually, G is more than E also. So sort of like insert E between G and H for that, or for the next 2, like ordering. But yeah, don't try to do more than that. You're just going to overexert yourself and you're just going to be very frustrated. And more than that, like maybe you can get the harder ones. Like I have been in situations where I spent hours and I was able to get the harder ones, but you're not learning as much from it as you would learn if you did something easier. So be sure to do that. And okay, I'm gonna say you're not going to sorry. When I say you're not learning as much as you would if you did something like easier, I mean like there's something more closer to your level. If you're a little serious, problems like right above here, you're gonna learn a lot. Try stuff here, you might get it, but you're not gonna learn as much, and you're also going to do a lot fewer of those problems, right? You're not going to do a bunch of problems here. It's just takes way too long. If you do problems here, you can do a lot of them. So yeah, do those, and then once you get better, maybe you can come back to this contest, come back to this stream, and try to get like the next 2, and that's awesome. But for now, just do 2 what we did before. Yeah, if you have any recommendations on future videos, future contests you want me to work on, any questions, comments about coding in general, be sure to leave them in the comments, and I will read my comments. So just do that, and yeah, hope this helped. See you later. Bye.